Okay, in this example, we're going to look at a block of lead floating in a pool of mercury, and specifically, we're going to look at what happens to that floating lead when the temperature of the system increases. So this is a thermal expansion problem with the added concept of buoyancy. In part A, we are asked what fraction of the lead is submerged in the mercury. Okay, so this is before any thermal expansion has occurred, so this is a simple buoyancy problem. So we need only consider the situation drawn here, the free body diagram that shows the lead floating in the mercury. It is partially submerged, so it has a fraction of its volume that is submerged. And we can find that by considering the gravitational force and the buoyant force. And here we have the sum of forces in the y direction, y shown here, positive y pointing upwards. That we have the buoyant force and the gravitational force. We have equilibrium because the object is floating, so it is not actively sinking and accelerating. We plug in the buoyant force, which is the density of the fluid, the volume displaced, and gravity. And then the gravitational force acting on the lead is obviously just m, shown here. Right, so this value right here is exactly equal to the mass of the lead. All right, so mass of the lead, okay, times g to get gravitational force. We see the g is in both terms, so it cancels out. And so then we are set up to solve for the volume that is submerged. So here, doing the algebra, we can solve for the volume displaced, which is equal to the volume submerged, because it's the volume displaced mercury, which is equal to the volume of submerged lead. And when we do that, we find that it's just the density of lead times the volume of lead divided by the density of mercury, which ends up being 0.38 cubic meters. Okay, and of course then we can see, fractionally, if we were interested to compare that, we could look at that the original volume of the lead was 0.45, so it's a pretty good portion of the lead, right? So it's floating pretty low in the mercury, but it is not sinking. To specifically show the value of the fraction of the lead submerged, we can calculate it as so, the volume submerged over the volume of the object, which is the volume of the lead, and we find that 0.84 of the lead is actually submerged. So moving on to part B, we were asked a arguably more complex question, and one that does involve thermal expansion. And that question is, how much would the system need to be heated for the fraction of lead submerged to increase by 10%? So in this case, we'd be going from 0.84 to 0.94. But we're more interested in the difference rather than the absolute change from 84% of it being submerged to 94%. Okay, so what would that look like? All right, so let's look at our first step in this process. All right, so we're going to actually set up the fractional change formula here. All right, so in general form, the fractional change would be the new fraction minus the old fraction divided by the old fraction. All right, that gives us the change. Okay, so the original fraction of the lead we would have, so there is just the volume submerged over the volume of lead. Okay, so that's what we solve for. That is our 0.84. Now we have the new is the heated. So it would be the volume heated submerged. Okay, so that's the volume of heated lead divided by the volume of the total volume of heated lead divided is in the denominator, and then the volume of heated submerged is in the numerator. So how do we deal with that heated submerged and heated lead? Heated lead seems easy enough. It's simply going to be the total volume of the lead. But how do we calculate heated submerged? Well, we have to find the new fraction that floats with after thermal expansion, because the important thing here is that the mercury and the lead are not thermally expanding at the same rate. If we look at the volumetric expansion of mercury, it's 18 times 10 to the negative 5. If we look at the linear expansion of lead, it's 2.9 times 10 to the negative 5. Well, the relationship between linear and volumetric, well, B equals 3 alpha. All right, so the volumetric expansion of the lead is just going to be 3 times 2.9, so about 9, which is still significantly lower than mercury. So in other words, the mercury is expanding about twice as fast as the lead is. So that means that the same amount of lead is not going to float above the surface. What's actually going to happen is that the density of the mercury is going to be decreasing at a greater rate than the density of the lead. Because when they both thermally expand, when anything thermally expands, its density decreases because it gets a greater volume for the same amount of mass. So the density of lead is decreasing, the density of mercury is decreasing. But mercury is staying denser as the temperature changes, which means that the mercury should start to sink deeper into the lead. Okay? So then finally, since we were asked for a 10% increase in this formula as a ratio, it should show up as 0.1. Now we could multiply the left-hand side of the equation by 100, right? We could have 100 over here, in which case this would become 10, but we will leave it in fractional form, okay, rather than percentage form. Okay, so let's look at the next step. So the next step that we'll take in this calculation is changing our fraction submerged formula, or a change in fraction submerged formula. And so the section I have circled here in green is representing the correct formulas now taking into account temperature. So what's happened here? Well, the volume heated submerged has become dependent on the volumetric expansion rate of mercury, the change in temperature, and we have simply that's basically this is the volume of displaced fluid. Okay, so both of these you can see I have in black here. I wrote volume expanded. So this term up here, the volume of heated submerged is also the volume displaced. All right. So let's make this clear, maybe with a better label here. I'm going to call this, instead of this volume expanded, it's going to be volume displaced expanded. And that's why, if you think about it, that this term in the numerator, what I call heated submerged, is really the volume of mercury. That's why we have the material dependent term for mercury show up in the numerator. Whereas the heated lead, well, that's entirely dependent on the lead, so mercury is not relevant there, and we're only looking at the thermal expansion rate of lead. Okay, so that's how we change both the expressions. All right, so now it's a matter of solving for delta T. So we're going to continue with our solution, algebraic solution of delta T. So here I'm just manipulating the equation to set up for it. Okay, so you see that I make a simplification shown here, or rather a cancellation across terms in the overall numerator. So the overall numerator here and the overall denominator, and that cancellation is shown with the gray lines. Right, so this one here. So these cancellations. Okay, and so when we do that, the expression becomes this here, and we can further simplify in our pursuit of solving for delta T. All right, so our final step of solving for delta T, all right, it's just some further algebra shown here. All right, and then finally solving for delta T, we end up with 0.1, our fractional change, the coefficient of volumetric expansion of mercury, minus 3.3 times the linear expansion of lead, right? And that 3.3 came out of simply dividing 3 by 1.1, okay, or rather multiplying 3 by 1.1. All right, and again that was so that, in other words, the 3.3 is kind of distributing the fractional change in there. But when we find, so but this is a somewhat general form of what the expression should look like, and in this particular case, since it was 0.1. I guess another way to think about this is we could have, this could be any change. So if it was just, that would be our percentage, or rather our fractional change, and this would be 3 times the fractional change if we wanted to keep it in a more general form. So, okay, and 3 times fractional change right here. But again, in this particular case, we get 1,190 Kelvin as our temperature change. So whatever, it doesn't matter what the system started at, it only matters that it changed. And I guess I should say it somewhat matters what the system started at, because we were given a certain density of mercury, and that was presumably looked up from some table, likewise for lead, and usually tables of densities are for 20 degrees Celsius. Right, so we started at 20 degrees Celsius, we heated up to some 1,190 degrees Celsius. So you have to get the system very hot to have such a substantial fractional change for the lead to sink that much further. Almost completely sink, go from 84% submerged to 94% submerged. All right, and of course, if you continue to heat up the system enough and didn't reach the melting point of lead, which is luckily above 1,190 Kelvin, so we are physically accurate in that sense. But as long as you stayed beneath the melting point of lead, you could perhaps, depending on where that melting point is, get to a point where the lead would actually begin to sink because its density would be greater than that of mercury. All right, thank you.